In chapter 12.7, we begin to talk about the heating curve for water. There are 5 segments in the transition of ice, liquid, and gas. First, ice begins to warm up with no phase transition until it reaches its melting point. It then begins to transition into a liquid. The liquid water begins to warm up until it reaches its boiling point. After reaching the boiling point, the liquid water begins to vaporize into steam. The last phase will show steam warming up. A heating curve displays the temperature of a substance. As heat is added in our heating curve, we will see how water undergoes phase transitions from a solid to a liquid and then from a liquid to a gas. In our example, we will begin our curve with an ice cube with 1 mole of water at negative 25 degrees Celsius. When we apply heat, its temperature rises in accordance with its heat capacity. In the first segment, solid ice is warmed from negative 25 degrees Celsius to 0 degrees Celsius. Since no transition between states occurs here, the amount of heat required to heat the solid ice is given by mass times heat capacity times the change in temperature. The heat capacity of ice is 2.09 joules per gram degree Celsius. The mass is equal to 18 grams and the change in temperature is negative 25 degrees. Our calculations show us that we need 941 joules or 0.941 kilojoules of heat to warm ice from negative 25 degrees Celsius to 0 degrees Celsius. In segment 2, the added heat does not change the temperature of the ice and water mixture because the heat is being absorbed by the transition from solid to liquid. The amount of heat required to convert it into liquid water is given by the number of moles of water times the heat of fusion. Our calculations show us that we need 6.02 kilojoules of heat to melt the ice into liquid water. In segment 3, the liquid water warms from 0 degrees Celsius to 100 degrees Celsius. Since no transition takes place during this segment, we use the same formula from the first segment and multiply the mass times the heat capacity times the change in temperature. Since the heat capacity of liquid water is 4.18 joules per gram degree Celsius, our calculation should give us 7.52 kilojoules of heat in order to warm the liquid water from 0 degrees Celsius to 100 degrees Celsius. In segment 4, water goes through a second transition, this time from a liquid to a gas. We use the number of moles times the heat of vaporization of water, which is 40.7 kilojoules per mole, to find the amount of heat required to convert liquid water to steam. We should get 40.7 kilojoules of heat as our answer. In segment 5, steam warms up from 100 degrees Celsius to 125 degrees Celsius. Since no transition occurs during this segment, we multiply the mass times the heat capacity of steam times the change in temperature. The heat capacity of steam is 2.01 joules per gram degree Celsius. Our calculations tell us that we need 905 joules or 0.905 kilojoules of heat to warm steam from 100 degrees Celsius to 125 degrees Celsius. Okay, pop quiz. How much energy in kilojoules is required to completely vaporize 200 grams of 25 degrees Celsius liquid water? So we use what we learned in segment 3 and find out how much heat is needed for 200 grams of liquid water to reach its boiling point. And we should get around 62.760 kilojoules. And then we find out the amount of energy required to vaporize 200 grams of liquid water, which should get us around 451 kilojoules. We add all these energies together, and our answer should around about 515 kilojoules.